Another important concept is consensus. So we've talked about, in very general terms, something called proof of work, where miners are doing the work to find that rare hash that will be linking one block to another block. But basically, this is a key ingredient for blockchain technology. So this is the mechanism whereby all of the nodes in the network agree on the historical blockchain. Right? So it's really fundamental that we have to have some sort of agreement. So again, the two main technologies are proof of work and proof of stake, but as we'll see, there's many different versions of this. So even consensus, just to define it, is difficult. So you could have majority, let's say 51%. You can have supermajority, you can have unanimous. It might be that not all votes are equally weighted, depending upon what you're doing. So this is like an ongoing issue to figure out what the ideal consensus mechanism actually is. So we need consensus because we don't have a centralized leader. So if you were centralized, somebody would just decide. But that's not the case in decentralized finance. So you have to do this in a way also that we kind of prevent kind of untrustworthy parties from kind of dominating the consensus. Because if that happens, then the protocol will fail. People will not have any confidence in it. So, so basically what we're doing is agreeing upon, think of it as the new blocks, right? So there has to be agreement, and the new block basically is added to a chain that people agree upon. So, and of course, within the block, the transactions have to be valid transactions, or the block isn't a credible block. So somehow consensus has to be achieved, and it's not achieved with human oversight. So there's no, again, central leader. And one way I think it's good to think about this is that once this is decided, it's irreversible. Okay, so you come to consensus, you can't change your mind. Given the nature of this technology, that once the transaction makes its way into the blockchain that's relevant for, let's say, Ethereum, then it's there forever. You get one shot at this. So it's really important to get this right. So this is distributed system consensus. There's a lot of research on this. It is still fairly early on, but I like the very simple definition here, that consensus is the process by which all nodes agree on the same ledger. Okay, so it's got to have certain properties. It's got to be, resistant to attacks by malicious actors. And again, there's many different ways to actually do this. So it's also interesting in the world of decentralized finance that we can have consensus where parties agree, but you don't need to trust the other party. Indeed, you don't even need to know who they are. So this is very unique. You think about, for example, a government vote or a consensus. You know exactly who voted for what. And you might know that somebody is trustworthy or not trustworthy. This is a completely different situation. Okay, so this is essential, that we don't need to trust other parties to come up with a consensus. So we're going to verify transactions without trust. Okay, indeed, within the system, anybody can be running a node. It doesn't matter who you are. Indeed, I've told you that it is technologically infeasible to go in and mess with the Bitcoin or Ethereum blockchain. And a hacker would be much better just setting up a node. Okay, so the hacker might be somebody that's completely not trustworthy, but they're running a node, and you don't care. Okay, so because their incentive is not to attack the network, but effectively just to join and to profit from it. So again, there's various different different types of consensus that we'll talk about, and this is a key component in terms of what we do. And there is, I guess, agreement in terms of consensus right now between Ethereum and Bitcoin's blockchain, but that will change. And again, we'll take a look at these different technologies. So one technology we've talked about already is proof of work. Like I said, and again, it doesn't matter who is doing that work. We don't need to trust the miners doing the work. They just need to produce that really rare cryptographic hash. Okay, so those miners are assembling transactions, verifying the transactions, and then searching for the rare cryptographic hash. Okay, so it is when they find the nonce that delivers that hash, it is very easy for anybody to verify that that hash has a lot of leading zeros. That's a rare hash. So verification is really easy to do. And again, the miner is pulling the transactions from the memory pool, picking the most valuable ones first, and then cycling through different nonces to get this really rare hash. When they win, they get a reward. They get a reward in Ethereum, they get a reward in Bitcoin, and of course, part of the funds that they get is from the transaction fees that are within this process. So again, you can have a node that is doing mining. So that's possible. Or you can just have a node that's not doing any mining, but just has a copy of the Ethereum blockchain on it and is providing service to the network. So you don't have to be doing mining if you're a node. So the way it actually works with the proof of work is the miner will search for that rare hash. If they find it, they will broadcast it to the network. And as people, or as the nodes on the network verify that the hash is associated with the nonce and the transactions, that actually works, then they add that to their copy. They add that block, that candidate block, to their copy of the blockchain, whether it's a Bitcoin or Ethereum. So it kind of propagates through the network. In Bitcoin, this happens every 10 minutes. Ethereum is much faster to actually happen. So, and as soon as that new block goes into a blockchain, then we start the process again, going through the different transactions. So in terms of strengths and weaknesses here, proof of work is very straightforward. It's proven to be extremely reliable. Okay, and we can have a lot of predictability in terms of the block times. If a lot of computing power comes onto the network and that rare hash is found faster than, let's say, 10 minutes in Bitcoin, then the difficulty just adjusts to make it more difficult. Or if computing power goes off. So for example, China shuts down some mining operations. Well, then it takes a lot longer to find that difficult hash. And then the algorithm just adjusts the difficulty. So it makes it easier. and we stick to the time for the blocks. So again, this is pretty straightforward. It is, of course, vulnerable to a 51% attack, but I've already argued that that just doesn't make any sense in terms of the money that would have to be spent to amass the computing power. And then even if you did that, what are you going to do? Are you going to send some crypto to yourself? Because if you do that, given that you've amassed 51%, nobody will have any confidence in the crypto, and the price will likely go to zero. So even after spending all of the money and amassing all the technology, even if you could pull that off, you're going to destroy the value of the actual crypto. So the only way that makes sense is if there was a national or international actor that wanted to drive the price to zero. Okay, so it's vulnerable technically, but for strong blockchains, it's just not that feasible. So there are, considerable strengths. This is very secure in terms of the amount of computing power that's necessary. But in terms of drawbacks, it's an enormous waste of resources. So Bitcoin, for example, uses the same amount of power as Argentina. Much of the power is by fossil fuel, which is just not a good idea. We'll talk about this later in course 4 in terms of environmental risk, where I will go through and show you a calculation of how much carbon offset you would have to buy to offset the carbon created by the mining of one Bitcoin, just one. Okay, so this is a disadvantage also. The hardware is very specialized. So the hardware that I showed you in course 1, that's in the basement at Duke University, the S17 miner, it does one thing, SHA-256. It's hardwired in, and that's what an ASIC is. It's a specialized chip that does one thing. And the E3 miner does one thing, and that is the KCOC-256, and it's designed to do that. The S17 does 53 terahashes per second. Okay, that's all it does. So it's specialized, and you could think, well, maybe that hardware could be used for better purposes. So in a way, the proof of work is got a lot of strengths, but it does have weaknesses, and indeed, there are other weaknesses. So the scalability issue, there's just not enough transactions per second to be competitive. So that is a problem. And that's a reason Ethereum is moving to proof of stake. It's one of the reasons that we can do far higher throughput. The other thing with proof of work is that the miners really aren't invested in the system. They win their Bitcoin or Ethereum and usually just dump it immediately. So they're providing a service, but they're not really a stakeholder in the sense of holding the actual currency. So again, proof of work is out there, but there's also going to be a transition to proof of stake. I put Ethereum 2.0 there, where Ethereum 2.0 means a movement to a proof of stake. Okay, so what is proof of stake? So proof of stake is, instead of everybody doing the mining, so think of thousands of machines cycling through and doing the mining. What about just delegating to one miner? So choose somebody at random. And indeed, why not do that in a way where it makes sense for the system? So instead of just a random miner being chosen, why not have it based upon the size of either the holdings or a stake? So you put up some Ethereum and you stake it, and you look at all of those that have staked. And let's say that I put up 10% of what's staked. And then probabilistically, I will be tapped on the shoulder, designated to mine about 10% of the time. Okay, so this is a very nice idea in that what it does is it eliminates all of this redundant mining. So you still go through some of the same steps in terms of hashing, but this is way more energy friendly to actually do. So there's various different aspects to this. And one aspect that's interesting is that there's not the redundancy, as I've mentioned, but there could be this extra incentive in terms of the stake. So you actually, given that you've got a stake, you're invested in the currency, that you are incented to do the right thing. So, for example, suppose you did the wrong thing, that you grab some transactions from the memory pool, and one of the transactions is a bogus transaction. And then you propose that block. And think of the following, that because you made a mistake and you put an invalid transaction in, then we reduce your stake. So you got to pay for it. So you got to cover the cost. Okay, so again, this makes it very compatible to do the right thing, because of course, you're being rewarded when you get designated, but you actually are incented to do the right thing because you've got a stake. So this is proof of stake, and it's got a lot of advantages, no useless mining. Indeed, there's not really a reason to have this competitive hardware advantage. So this could be just a regular computer rather than a specialized ASIC miner. And it's compatible in that that those with the biggest stake, they are most probable to be designated to mine, but they also have the most to lose. Okay, so the incentives are aligned. So good idea. It's also this idea of the 51% attack doesn't make any sense in terms of proof of stake. So it makes sense in proof of work, but not proof of stake. We've got a designated miner that will be assigned to add the next block. So this is far more efficient than proof of work. And there are many blockchains that exist today that use proof of stake. So this is not without risk. And theoretically, it encourages centralization. So think of it this way. The miners with the most, or the actors within this network that have the most Ethereum, they're most likely to be chosen to do the mining and most likely to get the reward for it. So effectively, the rich get richer. And it's possible that this could lead to more centralization. So that is a well-known drawback. Some people claim that the security of proof of stake is not as good as proof of work, but I think some of these claims are by people that have an interest in kind of maintaining a particular consensus mechanism. So, for example, a Bitcoin miner has no incentive to change to proof of stake because all of their investment in their computing machines would go basically to zero. Okay, so I don't think that this is really a drawback. So just to close here, I've talked about proof of work, I've talked about proof of stake, but there's many other iterations. So for example, delegated proof of stake. So it's a very interesting idea that I might have a small amount of Ether, but I can delegate some of that to somebody else so that they actually build up a bigger stake. And then I share in the rewards when they're designated to do the block. So a good idea. There's delegated Byzantine fault tolerance, very popular in some commercial implementations of blockchain, proof of capacity, proof of elapsed time, proof of identity, proof of authority, proof of activity. There are so many of these candidate mechanisms. And we'll see what actually happens. Again, this space is very early. We started with proof of work. Now we've got a number of different candidate consensus mechanisms. Even within proof of stake, there's many different ways to actually do that. But there will be a transition. For almost all of the cryptos, there will be a transition to something like proof of work to mitigate that problem, which I consider a very serious problem, the environmental problem. Bitcoin will stick to proof of work. And we'll talk about that risk a little later on in the fourth course.